Good afternoon, everyone. My name is TJ Willits with Veolia Water Technologies. I'd like to welcome you to today's Veolia Water Tech Talk entitled Plug and Play Odor Control, specific for H2S, how it relates to both municipal and industrial facilities. Just to go over some housekeeping items for today. Obviously, you should be hearing me speak now. There's two ways to listen into the audio for today's broadcast. The first one, which is probably most of what you're doing there, is listening through your computer speakers or headphones. If there are any issues with that option, you could also toggle over and pick the phone call option, and you could go ahead and use a call in, like a conference call number. Just to let everyone know, their microphones are automatically muted, and the webinar will be recorded and it'll be sent out for those who register for the webinar within 24 to 48 hours after the broadcast. And even though everyone's microphones are muted, we want to make this as interactive as possible. We have some time at the end of the presentation to go through some questions. So at any time throughout the broadcast, just go ahead and type that into the question panel. It should be on the right side of your screen. Go ahead and type it in there, and we'll try to queue those questions up and get through as many as possible after the broadcast. Just to let everyone know too, this is a live webinar broadcast. If you're watching with us, we also have 60+ webinars on demand, and that's available at our website, veoliawatertech.com. So head over there if you want to go and browse some of the other topics that we have related to water and wastewater treatment. And for those that are attending, if you need a participation certificate for continuing education, those will be emailed if you're attending the live broadcast. They'll be sent out 1 to 2 days after the webinar. Maybe check your spam filter if you haven't seen it, but be on the lookout for that after the broadcast. And also something that's a little bit of fun, right after the broadcast, you'll be taken to a short survey. It should take a minute or two. For those that go ahead and take that survey and fill in all those fields, we're going to put you in for a raffle to win an Amazon gift card, and we'll let you know a day or two after the event if you've won. And before we get into the technical portion, just a little bit about Veolia Water Technologies if you are unfamiliar with our company. But really, water and wastewater is our key focus, and we do that by helping customers with projects, technologies, and the services that support by putting together those processes and projects and that utilize our various technologies. And what we do is we do support several different markets. You can see them listed there on the screen. But of course, we work with both municipal and industrial customers from a variety of different industries. And we're going to transition to our technical portion of the presentation. Before we meet our panelists for today, our specialists, just to go over what we're going to accomplish today. We're going to go over some of the background items related to H2S, the risks, costs from those odors. After that, we're going to go and look at some of the various ways that people are commonly treating for odors in H2S. Then following that, we're going to introduce you to the technology that we're talking about today. It's called the hydrogen sulfide elimination system. You'll hear it called HSES or HSES. And we're going to introduce you a little bit about what we're doing for helping municipal and industrial clients with their H2S. And then we're going to take you to review some real world case studies of how we've helped clients with their particular odor control issues. And then we'll go over some final things like the first steps in executing an odor control project. And then, like I said, we'll have some time for Q&A and wrap up after today's presentation. And now I'd like to introduce you to our panelists for today. Our specialist, Phil Mateo, is an applications manager here at Veolia Water Technologies. Phil has been providing technical support to both industrial and municipal customers and has over 33 years of water treatment experience. And specifically, he has 15 years experience specifically related to H2S and odor control treatments. Very unique. Phil's primary focus is chemical treatment within water and wastewater and cooling systems, and also supports automation equipment needs related to that. Phil has a bachelor's degree in chemistry from Syracuse, and he also has an MBA from that institution as well. So I'm going to hand the broadcast over to Phil for him to take you through some issues related to odor control. Are you with us, Phil?
I am. Thanks, TJ. So first, let's start by spending some time learning about H2S, how it's formed, and what its dangers are. So first off, where is H2S typically found? In the municipal industry, it can be found in any portion of a collection system from the sewers in your neighborhood all the way to the wastewater treatment plant process and even into the sludge handling. In the industrial sector, it's much the same. It's found in most industries that produce a wastewater stream, such as refineries and chemical plants, pulp and paper mills, certainly the food plants, ethanol, even landfills. Bottom line, any facility that produces a wastewater stream can have H2S issues. So what is H2S? H2S is the common name for hydrogen sulfide. It's a colorless gas that's heavier than air, and it likes to settle to the bottom of rail cars, treatment tanks, sumps, and pits. This makes it an invisible danger to the unsuspecting personnel. It's created by sulfate-reducing bacteria, SRBs, who produce sulfate to sulfide in an anaerobic or anoxic environment. It can also be produced chemically in certain industries. The sulfide in the water then escapes from the water into the air in the form of a hydrogen sulfide gas. And most people recognize H2S due to its rotten egg odor. So how does it form? Again, it can be produced in certain industrial applications, or it can be produced biologically. Sulfide forms biologically when dissolved oxygen levels in the water drop below 1 milligram per liter. Certain bacteria utilize sulfate as an oxygen source when the DO is too low. When the sulfate molecule is reduced by the bacteria, it becomes a sulfide. This bacteria is known as sulfate-reducing bacteria, or SRBs for short. Sulfide remains in the solution even when the DO levels rise up higher than 1 milligram per liter. Sulfide is always in solution. There could be no H2S in the atmosphere until sulfide has formed in the solution. When we mention H2S formation, what we're really discussing is 3 species of H2S. And that's the H2S itself as a dissolved ion, hydrosulfide, and sulfides. And they all contain the sulfur molecule. The graph on the upper right shows the percent of each species at various pHs. The lower the pH favors the formation of H2S, which is the red line. A higher pH favors the formation of sulfide, which is the blue line. The graph in the lower left shows the equilibrium that occurs in a water solution between the 3 species, the H2S, the hydrosulfide, and the sulfide. And again, that's directly related to the pH. But only one of these 3 species can off-gas, and that is the H2S dissolved, can off-gas as H2S as a gas and get into the air. The temperature also has an effect on H2S. As temperatures rise, H2S can escape solutions more easily. And as temperatures in the air and water rise, the DO level in the water typically decreases, leading to increased sulfide and H2S formation. This is why odor complaints and corrosion levels are magnified during the warmer months. Now, the amount of H2S in the gas is H2S gas in the air is proportional to the amount of H2S dissolved in the water. Even a small amount of H2S dissolved in water can produce dangerous levels of H2S in the air. For instance, the results of one study show that at room temperature, even 1 ppm of H2S dissolved in water can produce greater than 200 ppm of H2S in the air. So the bottom line is a little bit of H2S in the water can create a bunch of H2S in the air. So let's discuss what that does. Let's just discuss the effects of H2S on humans. The chart on the left shows the health effects of H2S in the air on the human body as you breathe it in. And at very, very low levels, below detectable levels, your nose will smell it. And then as it gets up, it gets more and more problematic to the point that you could get headaches, nausea, your throat will start to burn, your eyes will start to burn. You can get to the point where you start to lose your sense of smell. And that's very dangerous because humans rely on their sense of smell to tell them something is wrong. So you'll have olfactory paralysis. And it doesn't take much to literally create a situation that where people die. So H2S can be very dangerous depending on what the level is. So at 1 ppm, you're going to be in the neighborhood of olfactory paralysis, respiratory tract irritation, and things like that. Excuse me 1 second. On a side note, at Veolia, we require all our personnel working in the field to carry a 4-gas detector. H2S is just one of them. We never trust our sense of smell to keep us safe, and we recommend that you do the same. So where else can H2S have an effect? Shown here is a typical situation in a municipal or industrial sewer system, aka a collection system. Below the water line, bacteria will live that will convert the sulfate to H2S, and some of that H2S will off gas. And in the crown of the pipe or the top of tanks, you will have a different type of bacteria that will live in that warm, wet environment, thiobacillus bacteria. And they will literally take the H2S gas and consume it. And as they do that, they will excrete sulfuric acid. The sulfuric acid then will corrode the metal or concrete crown of the pipe, causing that pipe to fail. Not only that, but copper components in the electrical systems in most operations can also be oxidized and eventually rusting to the point that they have to be replaced. The chart on the left is from the EPA, and it shows the relative life expectancy of pipe in various H2S environments. And I know this can be debated back and forth, but at the macro level, what it's basically saying is a 1 ppm of H2S there in that environment, your pipe should last 25 to 50 years. But if you go up to like 5 ppm, you're going to be down around 5 years of expected life. And while we can debate how accurate this is, the bottom line is the effects on both concrete and on iron piping is pretty severe. And these pictures on the right show piping that is corroded both on the outside and on the inside. The one next to it is actually a sump. They even tried to seal this sump with a spray liner that corroded. Obviously, this pipe here has corroded both from the inside and the outside. And especially in the municipal sector, one of the great risks is when these pipes fail, if they're underground, if they're underneath the road, you have a good chance of having a very dangerous condition occurs as the ground just gives way. So how do we control odors caused by H2S? We typically see, let's say, 4 different common strategies for handling the H2S issues. Obviously, design is always better treatment. Design the system so no H2S is formed, no problem. But that's much easier to say than do. Once H2S is formed, many sites will capture the H2S-laden air and then remove or destroy the H2S. We call that capture and treat, or also known as vapor phase treatment. A third option is to chemically treat the water to prevent the formation of H2S or to remove it if it's already present. And then for the wastewater treatment plants with sludge handling, treating septic sludges with chemicals to remove or reduce the H2S is often needed. When and where possible, design engineers attempt to size all their system equipment perfectly to prevent H2S formation. They do this by keeping the water flowing to avoid anaerobic or anoxic conditions. Of course, they also have to design for future expansion or growth. So sometimes systems are intentionally oversized for tomorrow, leading to low flows and dead zones where H2S is created today. Where H2S cannot be prevented by sound engineering or for any other reason, the H2S laden air can be captured, then treated with various equipment solutions known as vapor phase treatments. For instance, carbon filters, where the dirty air is passed through an activated carbon bed, the carbon can absorb H2S and also some other melodious compounds efficiently with limited moving parts and no additional chemicals. The downside is that media lifespan could be greatly shortened if we have a combination of high H2S and or high humidity, which is pretty common in our environments. Another downside is that media in certain locations needs disposed of as a hazardous waste. Chemical scrubbers such as wet pack scrubbers use caustic and chlorine bleach to capture and then destroy the odors, including H2S. Now, they can treat a wide range of reduced sulfur compounds, including mercaptans, at high airflow volumes. The downside is they do have a higher CapEx, require a constant stream of chemicals, and are susceptible to the formation of tenacious deposits in the sump and in the packed bed media. Additionally, caustic is hazardous and has a high freeze point, so it shouldn't really be stored outside without heat trace and insulation. Wet scrubbers are typically designed for 10 to 20 ppm H2S on average with 50 ppm peaks and are not meant to sufficiently treat levels of H2S much higher than that. Nail filters are used where dirty air is passed through a biodegradable bed of wood chips or something similar where special bacteria thrive. The wetted media captures the H2S gas and the bacteria literally eat it. This has limited chemicals are needed and are considered a green technology that can handle, let's say, 20 to 50 ppm of H2S. Media changeouts are not very often. They're very versatile, designed for removing various malodorous compounds, including H2S. One of the downsides is they do not handle load swings very well. The bacteria establish a very happy environment, and if we change the volume of H2S coming in either much higher or much lower, we can affect the bacteria living there. For a variety of reasons, chemical treatment may be the best option to prevent H2S issues either temporarily or permanently. We'll highlight the more common chemical treatments in the next few slides. For instance, the pH of the water can be driven higher using caustic or magnesium hydroxide slurry, thus reducing the amount of dissolved H2S in the water, which then reduces the volume of H2S gas released to the air. The majority of the sulfide species will remain in solution and are beneficial at the wastewater treatment plants downstream that are in need of some extra alkalinity. Downside is that the downstream untreated collection system laterals will be dropping untreated water and mixing it with our treated water, thus bringing the pH back to neutral. And as soon as that happens, the H2S will start to off gas. In any case, once this water hits the municipal water reclamation facility, they'll need to drop the pH back to neutral to protect the biological treatment itself. Another more inhibitory method is the feeding of calcium nitrate. This approach provides the existing SRBs with an oxygen source other than sulfate. Literally, we give them nitrate. If the sulfates are not used by the SRB, H2S will not be formed. It is easy to feed and safe to handle. Successful in multiple applications with less than 10 hours of hydraulic retention time, or RT. The downsides is it can require a very large volume of chemistry. You are continually feeding the bacteria with an oxygen source other than the sulfate, and the bugs get used to it and they grow and they flourish. There's an elevated OPEX, and it must be fed upstream of the sulfide formation zone to be effective. So multiple injection points may be needed. Lastly, because it promotes the growth, or it helps support the growth of those bacteria, it may exacerbate the fats, oils, and greases in wet wells as it promotes slime layer formation in pipes and in pits. A third method of H2S control is precipitating the dissolved H2S with iron salt, and that can be ferrous or ferric chlorides or sulfates. This iron sulfide precipitant is a very small black particulate that can be removed via sludge handling downstream. It is economical in a price per gallon for iron, and it works quickly. However, it does produce a large amount of solids, which eventually needs to be removed as sludge. It will all lower the pH of the water, potentially leading to increased infrastructure corrosion and more off-gassing of the remaining H2S. Another option is using oxidizers, such as chlorine bleach or other oxidizers. They can oxidize sulfides and some organics. However, they do require a large volume of chemistry, and they're not very efficient, as these oxidizers will react with any organics. And the typical wastewater stream, be it industrial or municipal, is full of organics that will increase the demand for the oxidizer. Hydrogen peroxide is another option. It is an oxidizer. It's a very strong oxidizer that oxidizes the sulfides and other compounds relatively quickly. And the only byproducts are dissolved oxygen, water, and sulfur. But it's non-preferential to the sulfides and will react with the majority of organics and inorganics in the water. So higher volumes may be required to treat H2S alone with a maximum HRT of just a few hours. And then there's the chemical scavengers they're sometimes used. These H2S scavengers are typically used in the oil and gas industries, and they work well there. They're more specific to H2S and also the mercaptans, but they're typically very expensive if the H2 levels are very high. Most municipal pretreatment coordinators are not familiar with these chemicals, and so approval to use these for odor control where this water enters the collection system may be difficult to get. Kind of as a sidebar, this is sludge treatment. Most wastewater treatment plants create some sort of sludge, either in the primary clarifier, biological treatments, DAFs, any of the equipment. This sludge is rarely 100% dry, so some of the water in the sludge may carry H2S in it, or SRBs will create H2S in sludge holding tanks. Since most of the sludge treatment involves belt presses or filter presses or centrifuges, the H2S is squeezed out of the sludge and into the air. Not only is this dangerous to the operators, it causes corrosion of copper and steel components and equipment. The treatment for H2S-laden sludge is nearly the same as for the water itself, but the ways we feed the chemistries and where we feed them is different. Common treatments include scavengers, various oxidants, as we already discussed, and precipitants. Now, for any treatment program for sludge, rapid removal of H2S in the sludge building is critical for employee health and safety and to protect the equipment. Many times we've gone into plants and find that the motor control center, the copper wires have turned black and have corroded, and that's due to H2S in the air. Regardless of any treatments that are used, care must be taken to ensure the treatment does not interfere with the coagulant and polymer flocculants used to help separate the sludge from the water. So, now that we understand the older chemical technologies used in the industry, let's discuss an alternative approach to handling H2S in water. Most professionals are familiar with Veolia as the largest water treatment technologies company in the world. We recognize the need for a chemical treatment approach to H2S reduction to complement and to protect our other systems. It had to be highly effective. It had to be specific for H2S. It needed to be flexible enough to be integrated with other technologies. And obviously, it's got to be economical and it has to be scalable. We call this approach the Hydrex sulfide elimination system, or HES for short. And for those that are unfamiliar, Hydrex is our global brand name for Veolia's line of chemical technology. So when you hear Hydrex, think of chemistry. The Hydrex sulfide elimination system is a patented technology that utilizes a special regenerative redox process to economically convert H2S into elemental sulfur. This final product, sulfur, is inert, it's not dangerous, and it will not revert back to H2S. And our approach is very specific to H2S. So the typical negative effects of high BOD or COD is reduced. So how does this system actually work? In the simplest terms, our process works in 2 steps. In the first step, our patented reactant oxidizes the dissolved sulfide, any of those 3 species. It oxidizes the dissolved sulfide, converting the sulfide into elemental sulfur. The Hydrex product is reduced and the sulfide is oxidized. Then in the next step, the Hydrex reactant is then oxidized by peroxide, or in some cases atmospheric oxygen, and it's thus called a regenerated reactant. The Hydrex is now free to attack more H2S. So in this step, the Hydrex is oxidized and is ready to do more work. And this redox, the reduction in oxidation happens again and again and again. And that's what makes this an economical approach versus other technologies. This is another representation of the process showing the H2S reduction in the lower graph, where you're starting at a high level and then it trails off. The sulfide conversion to sulfur occurs in minutes, and the regeneration process of the reactant can continue for hours. In the upper graph, we show the succession of steps that occur where we are oxidizing the sulfide, regenerating the reactant, oxidizing more sulfide, regenerating the reactant, until we have no more hydrogen sulfide left. And then that work is complete. Here is a picture of the sulfur that's pulled off using the HSES. I'm going to show a quick video that's an excerpt from a video you can find online at YouTube, on YouTube. Just Google Veolia. And in a minute, we're going to see that our feed system is fairly simple, with tanks or totes for the Hydrex reactant and the peroxide. We utilize specific chemical pumps compatible with these products. We typically utilize a simple PLC to control the pumps, and where possible, we flow paste the chemical pumps in line with the wastewater flow. The 2 products are introduced into the wastewater pipe or a vessel or a reaction tank in an area of good mixing. The first step will be the reaction of Hydrex with the sulfide, converting the dissolved sulfide into elemental sulfur. The next step is the regeneration of the Hydrex reactant by either peroxide or oxygen. And when peroxide is used, the only byproduct is water. This regenerated Hydrex reactant then goes back into the redox process again and again and again. So, talking about feed equipment, again, I said that this is fairly simple in design. We just need to be able to get the 2 chemistries fed into the system in a place of good mixing. And the various pictures here show different size tanks. Typically, the smaller tanks is the Hydrex, and larger tanks is the oxidizer that's going to regenerate the Hydrex. And then on the far right, you'll see a control that we use where actually it's a PLC that's monitoring H2S levels. In this particular case, it's monitoring H2S levels downstream and is sending information back to this controller that will then ramp up or ramp down the chemical pumps. We typically recommend conducting a pilot study of our treatment first. This allows us to see the true variability in H2S levels, flows, temperatures, etc., over different hours of the day, days of the week, and months of the year. This is much better than getting a single snapshot of field data, as no 2 days are ever the same when we deal with H2S and water. We can then develop more accurate plans for a permanent treatment. It also provides assurances to the client that the treatment will meet their objectives, and we will increase or decrease until we've hit their numbers, thus proving that it works, but also allowing us to build long-term estimates for the work. Another solution Veolia offers is the conversion of those existing wet pack scrubbers to our process. This neutral pH Hydrex solution is added to the scrubber sump in place of the caustic and chlorine. Scrubber is operated as normal with the Hydrex solution capturing and converting the H2S gas to sulfur. When this solution, Hydrex solution, is spent, it's discharged to the sewer or to the waste treatment plant. The charge typically lasts several weeks to a month. The beauty of this approach is that it will not scale up the scrubber packing, as we know is common in caustic chlorine systems. And of course, no more handling of the caustic nor the chlorine. So to summarize the benefits of our patented approach, it is highly selective to the sulfide, making it better than common commodity treatments. It's environmentally friendly as it's non-toxic and it is biodegradable. It's not harmful to the beneficial bacteria that are commonly downstream. It's safe to handle and easy to operate. This redox reaction is highly efficient, which is lowering our OpEx by allowing us to get more work done with less material. So we use lower volume of chemistry and lower dosage rates. That also reduces the amount of delivery and the labor and equipment and gives us a lower carbon footprint versus some of the more dilute solutions. We can definitely use the automated process control, sending signals back to DCSs and back to SCADA systems that will help our clients know what's happening in their systems. Now I will quickly share some case studies where we've utilized the Hydrex sulfide elimination system, both in municipal and industrial settings. We will, of course, not share the client's name or any other sensitive information. I'm going to keep it very general. In this project, it's a Midwest soy producer was experiencing both H2S odor complaints as well as physical damage to their process equipment in the plant. So both safety and equipment protection was important. Before our treatment, the H2S in the air above the water was over 1,000 ppm at injection point and over 20 ppm at the city's water reclamation facility downtown. These graphs are hard to see, but this is the data collected both before and after our treatment was applied. Initially, we're off the scale at greater than 1,000 and we could get it down to 0, and this is within the plant. Then the city headworks, we show how we were able to take it from in the 40s, take it down to 0. But in this particular case, it did not need to be perfect. And so we were able to reduce and optimize the program. And yes, we allowed more H2S to off gas, but it was within the restrictions of what the client needed. So it did this for economic reasons. Bottom line is the soy plant now has the equipment and operator protection it needed, and the city wastewater plant is happy that they aren't receiving H2S complaints at their headworks. This is a municipal application at lift stations out in the community. It's in the southern United States. Actually, it's in the Carolinas, where the weather here is typically very hot. The municipal client was receiving complaints from their citizens living near this lift station about H2S odors emanating. They also experienced some crown corrosion in their gravity main piping. The starting H2S level in the air were greater than 100 ppm at the downstream target lift station and over 200 ppm in a nearby manhole. This slide shows how we treated upstream in the system and then measured the results downstream. The goal was to reduce the complaints and better protect the system, which in this case meant H2S levels below 50 ppm after the treatment at that level within the wet wells. The complaints were eliminated and the infrastructure was better protected. This is another lift station, which is pretty common, in municipal, and this is in Florida. This project, the H2S control is needed in the collection system North Florida, actually Central Florida. A wet well located in a busy retail shopping district was releasing H2S, causing repeated complaints by both the shoppers and the shop owners. The untreated water had H2S levels ranging from 400 ppm in the air to as high as 1,000 ppm in the air. Our treatment was applied to 2 upstream wet wells and then measured the results downstream at the targeted lift station. The goal was to reduce the complaints at lift station C and better protect the system, which in this case meant, again, getting the H2S levels to below 50 ppm after the treatment. The complaints were eliminated and the infrastructure was protected. This is the actual data that came off the data logger at lift station A where it started, and then downstream at lift station C. And it is interesting to show how we have the diurnal flow throughout the day. And you can definitely tell when the wastewater pumps, the lift station pumps are running more frequently, and when they really slow down during the nighttime hours. This next example, offensive odors in the belt press room were causing odor complaints in the administration building for this water reclamation facility. And this happened whenever they were pressing sludge, the nearby people in the admin building were complaining. But not only were there complaints, but likely some damage to any copper wiring and controls in that sludge building, along with any unpainted steel in the room. And that includes girders, the material for the belt press itself, piping, and anything else that was not protected by a protective coating. Our solution was simple. We replaced the chlorine product with our HSES. We installed a simple 2-pump, 2-tote delivery system of chemistry into the sludge line between the sludge holding tank and the press. The odor levels and the employee complaints were reduced significantly with no negative impact on the polymer usage or the percent solids of the sludge. This one is an industrial application, and it was slightly different, but this one was a true emergency. Here, a refinery had between 6 and 8 million gallons of H2S laden water to dispose of. The H2S levels in various storage tanks range from a few thousand ppm to one tank with greater than 40,000 ppm in the air above the water. Production could not start back up until the water was disposed of and those storage tanks were returned to service. So needless to say, the H2S had to be eliminated before that water could be safely disposed of. Within days of notification, Veolia had a team of operators, feed equipment, and chemical on its way. The process we used involved feeding thousands of gallons of hydroxide peroxide to a storage tank that was retrofitted to be an extremely large batch treatment tank. The water was recirculated 24 hours a day for several days while the HSES was added. Then the H2S in the air above the water, samples were taken and we measured the H2S coming off the treated water until we saw that it was less than 1 part per million. The water was then disposed of and a new batch was run. The project's still ongoing with more than 1 million gallons safely disposed of thus far. This last case study is also unique and it's in the industrial sector. In that this client needed the safe destruction of ethylene dichloride, EDC, that had gotten into their wastewater sumps and canals due to a spill. This material is too high in volume and in toxicity to send it to their waste treatment plant as it was concerned that the MBBR could not handle the spills. The biology could not handle this. We utilized the same 2 hydrox chemicals in such a way as to produce hydroxyl radicals, which is a form of advanced oxidation. Essentially, we created a neutral pH Fenton's reagent and used that to destroy the ethylene dichloride. Once the EDC was reduced, the water was then safe to send to the wastewater treatment plant for final treatment. Over the course of several weeks, the spilled EDC in water was successfully treated from levels with 200 parts per billion of the EDC down to less than 200 parts per billion, which is 90% reduction, making it safe for the MBBR. So, how does one get started in an odor control project. There are many factors to consider when exploring odor control options. The obvious ones are odor complaints, infrastructure problems, health and welfare of the community, health and safety of your own personnel, and protection of the utility assets. One needs to understand the equipment and the systems to be treated, so a good process flow diagram is critical. Decide what data is needed and how best to collect it. Finally, the actual data is collected and a thorough analysis of the data is conducted. When we run a project, we do the data gathering for our clients. We use sophisticated measuring and monitoring equipment. This includes special test equipment, data loggers, remote monitoring, etc. From top to bottom on here, we have COMETs, vacuum ampules for testing H2S and for testing peroxide. Over here, we have a hot colorimeter for measuring H2S. Down here, we have two different types of data logging H2S analyzers, H2S in air analyzers, one of which has remote output capability. Next to that, we actually have some of the outputs that come off of these data loggers. It's the graphs that we use. And so it'll do your H2S levels, it'll do temperature, it'll do a couple of other things with it. And then down below, wherever possible, we recommend remote monitoring, downstream monitoring to see that your effects are what you expect them to have. And the equipment for testing H2S in water or H2S in the air phase. And this is very important if you want to optimize and automate your feed system. In summary, Veolia now has a patented, safe, effective, and efficient chemical treatment of H2S issues wherever and whenever they are found. It's a novel approach. It's environmentally friendly and non-toxic and biodegradable. This redox reaction is truly wonderful. It's highly efficient, and that helps us lower the chemical spend. And simple implementation from the pilot studies we do to full-scale implementation is very, very easy. So with that said, TJ, back to you.
Yeah, great. Thanks so much, Phil, for sharing all that background information about H2S and some of the common ways people are treating it and introducing us to the HSS process there. Very interesting. I just want to remind everyone on the right-hand side of the screen, there's that question panel. Please go ahead and enter some questions in there. We'll give it a minute for you to type that in and we can get some queued up there. One question just to kick things off here, Phil, can you talk a little bit about the process and what it might need, what it might take to execute a pilot project for a lift station?
The way we typically approach it is the data gathering up front, and we'll work with the collection system engineers to get a good drawing of the layout, including where their equipment is, where the manholes are, where the lift station is, and what's upstream of them. And ask a lot of questions about what are they trying to achieve and where are they trying to achieve it. Oftentimes in municipal, this starts with people in the neighborhood, citizens complaining about the odors, and then the collection system managers have to then go out and talk to these people, find out what's going on. But part of that is determining if we're going to feed something, where are we going to feed it to achieve the results that we need at the downstream monitoring location. Then, as we mentioned earlier, we'll go out and do some wet testing of the water to see what the sulfides are in the water, what's the pH, and what else is in that water. And usually we'll hang a series of the acrologs, which is the H2S data loggers in different locations. And we let that go typically for, let's say, maybe a week or two, because we do want to see the differences. Wednesday is different than Sunday, and 2 o'clock in the morning is different than 2 o'clock in the afternoon. Based on the flow and the levels that we're seeing, we're then able to calculate what we believe is the treatment cost, and we will give a proposal to do a pilot study for a fixed amount of time with a fixed amount of dollar, and then when they give us the go ahead, we'll go ahead and bring our equipment in, bring our chemicals in, and we'll start the pilot. And then throughout the process, we tweak the chemical feed to achieve the results that we want. We don't want to overfeed the chemistry, but we need to feed enough to hit the objectives of the client. When all that is done, now the client has the information they need to say, okay, if we take this full scale, what's it going to cost and what does it entail?
Okay. Just some more questions came in there, so we'll try to get to them. Okay, this is an interesting question. Can you review as to how H2S air concentrations can reach into the low 100s from just 1 milligrams per liter of liquid phase concentration? Is this dynamic equilibrium partly due to the constant production of H2S in the liquid phase, maybe from underlying solids? Maybe just, there's a couple questions in there, but you could get to the gist of what they're looking for.
Yeah, sharing that graphic was always difficult because that's done under lab conditions, and we did not do that study. That is published information. But there's a whole lot of different variables as to how much of that H2S, 1 ppm of H2S dissolved in water, how much of that's going to get into the air. Certainly the pH and the temperature are 2 of the big ones, but turbulence and the height above the water line where monitoring is being done, and how easy is it for this gas to escape? Is this wide open, allowing us to off gas more, or is it in an enclosed vessel where there's just a little hole at the top? So those numbers are good to say, look, a little bit of H2S in the water produces a great deal of H2S in the air, but we usually try to rely more on what is the actual H2S in the air, and then we use that to drive our recommendations, because the H2S that gets into the air is the thing that we're really having to treat for.
Great. Another question that's interesting is, it talks about how strong odor components could be the result of organic sulfur rather than inorganic H2S. And can you talk about how the HSS system might work in those conditions?
So there's a number of different sulfides out there that this program will work for. So not just a typical H2S, but mercaptan, some disulfide, some other stuff. So if it's a sulfide form, we've had great success in treating them, unless it's a very, very special case where that material not something that's going to off gas. And if it can't off gas, then it's not an issue anyways. But the beauty of this is it's easy to test it, and then it's easy to demonstrate it in the lab, in a customer's lab that says, look, let's take your stuff, let's go ahead and do our treatment in the jar, show you that it'll take care of it. You take that water sample, you send it off for analysis, and that'll give you the confidence that it will remove those contaminants, remove or reduce those contaminants that you're worried about.
Okay. Another question is, it's actually a pretty specific question. It's related to how would this system, what kind of install how would that install look at like a pulp and paper facility that has aerated stabilization basins? Yeah,
so I've done projects where obviously the larger projects we have done as much as bringing in 10,000 gallon storage tanks with chemistry, and I have used line of sight and also used radio frequencies, I guess it is, to talk from a downstream monitoring location back up to a feed skid. So this is definitely scalable, and it's driven more or less, the size of the equipment is just driven by, how much water are you doing, and basically how many pounds of sulfide do we need to treat a day. And that's usually, a combination of the ppm in the water and how many gallons of water we're treating. So it's definitely scalable to the point you could put in 10,000 gallon storage tanks refilled with tanker trucks. And in pulp and paper specifically, I've also done some work where you can utilize this at the primary so that you reduce the loading downstream. And then there's some special things you can do with peroxide that's pretty cool too. You can use it to help cut down on your foaming, and you can use it to basically re-oxygenate septic waters, because peroxide added to septic water will decompose and give up oxygen. So I've done that in a pulp and paper mill as well.
Okay, great. Another question is, what do we do with the sulfur that falls out of solution? How's that managed at the POTW or even if for an industrial site, if they're doing pre-treatment on site, what does that look like?
Well, typically in the municipal sector, you have very, very large volumes of water and relatively lower H2S levels. And so therefore, the sulfur just flows along with the water, and it'll either drop out in the primary or it'll drop out, in the secondary or maybe even tertiary, but usually the primary. And it's a very, very small particulate. It's so much smaller than black pepper. So we usually don't get complaints that it's building up, but it does contribute more solids to the POTW, directly proportional to how much H2S you had. But usually I've never had anybody in the municipal POTWs complain that, wow, we're getting a whole bunch of sulfur coming in. It's usually at such small levels compared to all the other stuff in their water that they don't notice it.
Okay. A question is one I haven't heard of is any food grade or FDA approvals related to using HS chemistries?
No, because this is used in wastewater, and so as in any of the other facilities, this is not designed to be touching your process. It's not going to be touching your production equipment. It's not going to be part of your HACCP. It's going to be usually outside the plant. So therefore, we've never had to worry about it because it's considered a wastewater treatment as opposed to a process treatment.
Okay. Someone put a question out there. Is there SDS or safety data sheets available and, about the reagents? I could confirm that we have obviously all that for all of our chemistries. Looking through the list here of questions. Here's one. What level of H2S starts to cause damage to copper wiring? Do you happen to know that figure?
Yeah, no, there's not a hard number. Obviously, if you've got, let's say, a sludge press inside a room and the room is closed off and you've got, you got forced air and you're sucking the air out of the building and you've got maybe a scrubber or something, and that H2S, that air is turned over frequently, you may not get much or if any damage to copper components, especially inside the motor control centers and such. However, I've been in facilities where the belt press runs, the doors are wide open, there's no airflow, and I will I will take a penny, a copper penny, and I'll put it up on top of the cabinet for the MCC and come back a week later and you take a shiny penny and it'll turn to a black penny within a week or two. So it's hard to say specifically, but if people start thinking about this and they do have H2S, you can typically look around that room and you'll see the overhead supports, the roofing, the bare steel is rusting, and you go inside and you look at the MCC and you see that your copper wire is turning black. But I can't tell you exactly how much it takes to do it, but I've seen it just a couple of ppm in the air. I mean, you can smell it when you walk in and you can look around and see. So even at, 5 ppm, 10 ppm for sure, but it has to get to those components first.
Okay. A couple of people asked questions related to this. Can you talk a little bit about, choosing what method of treatment? You talked about capture and treat, with the air, or would you go upstream and try to remedy the problem upstream in solution? So how does one evaluate those options, and is there anything that's in terms of making it a better choice, one or the other?
Some of these are how bad is the problem and how much is it going to cost to do it chemically. Then some of it is, how long is this going to be needed? Is this a temporary project or is this a permanent project? A lot of H2S is a cause. There's an upset in a wastewater plant. There's an upset in an industrial wastewater facility. There's a spill. There's something else. And so the chemicals usually win because it's a quicker to implement and it's not a long-term high capital solution. If this is going to be a continuous ongoing problem with H2S, well, that's where the make versus buy decisions have to be done at the plant, and we can assist with scratching out what, some budgetary numbers. But oftentimes it comes down to is how long am I going to be dealing with this? How much cash do I have on hand to build new equipment? Do I just leave it this way because we're going to close down that operation and move someplace else? There's a whole lot of typical business decisions that go into that.
Okay. Just another question that came in here. Let me see if I can find it. What is the outlet target of Hydrex and PPB?
The amount of Hydrex, the reactant that would be in the outfall after the work is done, is going to be proportional to the amount of H2S we have. So we're not looking to create residuals. We're looking to see the results of the reduction in H2S. So it's more of a recipe of saying how much H2S do I have. Then we also kind of test to see how much interference from organics may be there, BOD, COD, and we'll come up with a target. But quite frankly, where the rubber meets the road is the actual pilot, where we get to see how it reacts over time, night and in the morning and in the afternoon, on a Sunday, on a Wednesday. But there's not like other chemistries that you say, hey, if you want good success, make sure you have 5 ppm in the outfall. It doesn't quite work that way.
Great. Well, good. Thank you so much for answering all those questions. I feel really appreciate that. We're just about at time, so we're going to conclude this webinar. But before we do, I just want to thank Phil for taking the time to prepare this presentation, sharing all the challenges that people are experiencing with H2S, and all those 15 years of experience that he brought to the table today. That was really beneficial to everyone here. And just, I want to remind everyone to take that survey at the end of the webinar. Remember about that Amazon gift card we put you in a drawing for if you take that survey. And lastly, I want to thank everyone who spent the time. This was a very, very well-attended webinar, one of our better ones that we host for our Veolia Water Tech Talk series. I just want to thank everyone that spent about an hour of their day to learn a little bit more about this application and the technology for odor control and H2S remediation. Really appreciate you joining us here. Again, my contact information was up on the screen. You'll probably get an email from me after the webinar as well. Feel free to reach out and we'll connect you to an expert to talk about your specific project. So again, I look forward to hearing from you, and please stay tuned to our webinar announcements in the future, and I hope to see you again soon. Thank you and have a great day. Take care.